So I said already to Paul, I was a little bit pushed for time this time, and I did ask beforehand what you kind of level you wanted, what you wanted me to do, and I think the message was quite clear that it was to get the basics, to get really people to understand what Multilevel Monte Carlo methods are. So I did take a short course that I gave that I've given a few times, but recently at Penn State University, and I had to shorten it because it was a short course. So I will. It's kind of a bit open-ended, but these slides I can make those slides available. And as I say here, this web page here contains the full slides for the short course, which was 2 times 1.5 hours. And you can find the details. So I will. It's kind of a bit open-ended. I will probably not get to the end, but I hope to get the message across. So the second thing to say is that this has been ongoing for over 10 years now, and I started it originally with Mike Giles, who kind of was one of the first, well, the first that really popularized it. There is some earlier work, but Mike really invented the Multilevel Monte Carlo method. And Aretha Tekentrip, who was my PhD student at the time, with who I started all this work. And then after that, we've collaborated with several people. So I'm going to set this whole thing in the context of uncertainty quantification, and then give you a very simple ODE example to describe the methodology, before hopefully leaving myself some time to describe it also in the context of PDEs. I sort of know roughly what Cephx people are working on, or at least used to, when Ian Duff was leading the group. And I know some of you by name still, and I know what Uli does, so I think I know roughly what your interests are. So we all know in this audience in particular that mathematical modeling is becoming ever more important, in particular in the form of differential equations, as one of the parts to study our environment, to develop new technology, and to study for medicine, in engineering, you name it. And the methods have reached quite a high level of maturity and sophistication. So on the context of solving PDEs, we're pretty much now just chipping away the edges and improving our methods. And there's a lot of software available. But what is currently very much at the heart of much research is that in most models, the input data is typically not known, or not known precisely. So you have uncertainties in parameters, in source terms, in the geometry, in boundary conditions. And it's important to get to understand and quantify this uncertainty. And to do this is more challenging or more computationally costly than just to solve one individual PDE. And so we need to come up with efficient methods, and Multilevel Monte Carlo methods are one particular way to try to do this. So here is a couple of examples of what I mean by uncertainty quantification. If you want to predict a storm hitting the coast, you don't need to know where in mean it arrives, because that will give you 1 point on the coast, which is not very likely that it's exactly going to hit there. So you want a certain cone in which the storm is predicted to progress in order to evacuate and to decide on measurements. Similarly, if you study contaminants in the ground, for example, radioactive waste stored underground, you do not know the subsurface exactly. You only know it at a few points where you've drilled into the ground, and therefore your predictions about how these contaminants will be moving around underground is uncertain. And then another example where I have a recent strong collaboration and big project is in the context of carbon fiber composite aerospace parts. For example, on this Airbus A350, the wings are made out of carbon fiber composites, and you need to know how to design them so that it can be certified without having risking it, the airplane dropping down, or the wing cracking or something. So what do we want to do now mathematically? We want to study a PDE that models the system. For example, if we are in the linear elastic regime of an aircraft wing, we would solve, for example, this PDE here, the linear elasticity equations. But the importance being that the tensor here, the stiffness tensor in a carbon fiber composite, will be highly complex. It will be layered. It will have anisotropies in different directions depending on the fiber directions. And it will, and this geometry of this layering of the fibers will, of course, be not precise. It will be uncertain. Similarly, the loading on the wing can be uncertain, and so can be the domain and the boundary conditions. So essentially, all the parts in my PDE may be uncertain, and I would like to now solve this PDE under this uncertainty, which means I kind of need to, you can already imagine you need to solve a few instances of this in order to understand the variability and to understand this uncertainty. But let's go to a simpler model problem, which is the sort of fruit fly of UQ. It's the diffusion equation with a variable diffusion coefficient A, which could be in the subsurface flow. This would be the permeability. In the error elasticity, this could be a simplified model of the error elastic behavior. And then typically you're not interested in the full PDE solution U, but you're interested in some quantity of interest, which could be the strength of the wing. When does it reach a certain maximum displacement, or it could be just some average of the pressure in the subsurface. So now how can we address uncertainty in A? So I'm going to focus mainly on uncertainty in A. There could be uncertainty in F as well, or in the domain, as I said. But if we want to address uncertainty, say, in A, how could we do this? We could say we could do a worst case analysis and say at most it will be epsilon away from some nominal coefficient A naught. And then I could just simply compute all possible A's that are in that ball around A naught, but that's obviously quite a challenging task, and it's also going to be pessimistic because certain values of A that are far away from A naught will most likely be less probable than others. And so a very common approach to do uncertainty quantification is a statistical one. So you essentially don't assume that all values in that ball are equally likely, but that you have a certain probability measure on the set of all possible coefficients. And then if you're interested in, as I said, in the quantity of interest of the PDE solution, you can think of it as just pushing forward the probability distribution on the coefficient to the probability distribution on this quantity of interest. So for the sake of this talk, just think of Q as being a scalar quantity. As I said, some average over some region. And you basically, all you're interested in is the probability distribution or the density, probability measure of this one random variable that you're interested in. But you're knowing its distribution, or this distribution is known to you only implicitly as a push forward of the distribution of this complicated, spatially varying diffusion coefficient. And so even though you're only, the task is quite simple, you just want a 1D probability distribution, you have to work with an infinite dimensional function valued random field in order to determine this Q properly. And then a second issue with this uncertainty propagation is that in this context that I've described now, we have kind of a priori fixed a probability measure on this set, and this may be subjective. This may not be really the truth. You may not have a good understanding of this probability distribution. And so these are issues which are addressed when one has data, and when one has data, for example, measurement somewhere else in the domain, where you not where you have access to some sensor or something, then you can condition your distribution. So you can condition this probability measure on this set S on the measured data. And that would then be an inverse problem or Bayesian inference problem. And that's what we typically call uncertainty quantification. So both of those involve finding a probability distribution of an quantity of interest under some uncertain parameters. In the first case, you're just pushing forward the uncertainty. In the second case, you're conditioning the probability measure on the input in order to get a lower uncertainty on the output. Today, I'm only gonna have time to focus on the first part, but the second part is equally important or even more so, and multi-level Monte Carlo can also be developed and analyzed for that setting. But I will leave you to read up on that, or we can follow that up in further communication. So this setting that I'm just describing is particularly important. So I'm saying this in the context of the advent and the craze about machine learning at the moment. In the context of physical biological systems where we don't typically have a lot of data, like in imaging or in autonomous car driving, you often have very sparse and noisy data, and so you really do want to marry this data with a good mathematical model that describes the system. And so in this context, it is really important to kind of have both the PDE model as well as the data kind of come together in a sort of data fusion or Bayesian learning, it's called sometimes, in order to get a better learning than purely from the data as in machine learning. But it asks us for efficient methodology, and it poses new challenges. So why is it so challenging? And I'm now stepping back again to this context of uncertainty propagation again. So purely, I assume I am given a distribution, probability distribution on my parameter. Why is it difficult to give you a probability distribution, or even just a mean or some moment of an output quantity of the PDE solution? Well, first of all, it's a function valued random variable. So A of x and omega is a random variable at every point x. I will talk about it in more detail later. It's a random variable at every point x in the domain, and the value of this field at every point x in the domain is correlated with the value at a point y in the domain. And so to sample from that in itself is already a difficult task, which was actually one of the main parts of the research that we did with Uli in our paper. The second thing, and this is what the main challenge for today is, once I have sampled from this field, so I have a spatial field AX omega, I still need to average over, or I need to do the quadrature. I need to, for example, compute the mean of a quantity of interest of u, of a function of u, over all possible fields A of x omega. And this is a high-dimensional quadrature problem. And this is where our multilevel Monte Carlo will come in. And then finally, and this I know has been a big focus in Surfax in the past, we need to actually, in order to do to compute the quantity of interest for one such sample A of x omega, we need to actually solve this PDE. And just solving this PDE in itself is already a challenging task. You need to solve it on a fairly fine mesh, and you need to have an efficient solver like multigrid methods, etc. So all three aspects are challenging, and they need to play together in an efficient way to give you an efficient methodology. So one more point regarding why it is expensive to even solve these systems, and why this is a high-dimensional quadrature problem. If you look at the typical example in subsurface flow, where you have the A representing the permeability, the diffusion coefficient underground, how easy it is for fluids to flow through the porous medium, then the typical soils that we're looking at, like a limestone or something, will have quite a low regularity variability in the diffusion coefficient, and it will vary over many orders of magnitude. So you will have regions where the diffusion coefficient is almost 1 million larger than nearby regions, and it will vary on a very small length scale. This means I need a finite element mesh to solve the PDE, and it means in order to represent the random function valued field on that domain, I need a large number of parameters. I need to parameterize my function valued random field with a large number of parameters, and this means I have a high-dimensional quadrature problem. I will not talk today about the sampling issues and about the high dimensionality, why it's such a high dimensional problem. Obviously, it is an infinite dimensional problem in its continuous setting because it's a function valued random variable. But here you can see if you parameterize it, there is things like very similar to Fourier expansion of these random fields. You see here that this example I gave you with the pollutant, with the radioactive waste disposal, the time it takes for some pollutant to reach a safety margin is critical for the assessment of the repository, and here you see a few curves which are CDFs, which are cumulative density functions of the output quantity of this time it takes to reach the boundary. And I just want you to focus on this bottom left corner here, where you see that if you take 30 parameters, m equals 30, that's the pink curve, or even m equals 100 parameters, which is the magenta, is the turquoise curve, then you are significantly underestimating the probability of this time, of it taking that time, which is with blue and black with 500 or 1,000 parameters, significantly larger. So when this is the critical part of the curve for this particular application, and you do really need to go into the hundreds of thousands to measure to model this accurately. Okay, so what is the challenge in terms of quadrature? So I told you already that we're gonna need to parameterize with S parameters. Sorry, S is the M from the previous slide. So we have a few hundred dimensional input parameter. We're discretizing on a finite element mesh with mesh size H. We end up getting a finite element solution, a vector of length mh, and then we're computing our quantity of interest, which I said for simplicity is just the scalar valued quantity of interest. But as I said before, these are all still functions of omega of the randomness, and so the expected value of this random variable q here is essentially an integral with respect to omega. And so we need to still do an integral of this, in the Monte Carlo setting, such an integral is simply done by averaging realizations. So the standard Monte Carlo estimator for sampling the expected value of this quantity of interest here is essentially take n calculations with your input random field, compute the quantity of interest for those n samples, and then just add them up and divide by n. So you just do a sample average. Then we know, and I will describe this in more detail below, then you do know that this sample average is in the limit as n goes to infinity, converges to the expected value of the same quantity that you're sampling here under the uncertain parameter omega. So basically, this estimator, as n goes to infinity, converges to the expected value of the quantity of interest. But the quantity of interest that we are sampling is computed with a fixed number of parameters s, and it's computed with a mesh of size mh. And so this is still an approximation. So expected value QHS is an approximation of what we're really interested in, which is the quantity of interest for the original PDE. And so what I've just tried to explain to you is that there's two approximations going on here. One being the approximation of our PDE and also the parameterization of the random input. And that is called typically the bias, because you're biasing your random field or model discrepancy, you could call it as well. But this is the numerical error I'm doing because I can only work with a finite mesh size and with a finite number of parameters. So if we assume that this does converge because we have a finite element method, for example, to solve this PDE, then we can assume that the quantity of interest, the functional of your PDE solution, for each realization of the parameter of the diffusion coefficient converges with a certain rate of the mesh size to the exact quantity of interest. So this is the assumption on the bias error, on the error coming from the numerical approximation of the PDE. And then secondly, we also have the error coming from this Monte Carlo averaging. Now, every sample, on the other hand, and this is now what many of you know and work on, is going to cost you the solution of a linear system with mh degrees of freedom, but it's a sparse system of equations. So if we can, for example, apply multigrid, then we can solve the system linearly or in a linear complexity with respect to the number of grid points. So in that case, this gamma would be equal to 1. Okay, so now I have our ingredients. So we have the growth of the cost with respect to gamma, with respect to h, the decrease of the discretization error with respect to h, which has rate alpha. And then finally, the error can be decomposed into the error coming from the sampling. So the Monte Carlo error, which is the first part here, and from this approximation error from the finite element method. And if I want both of those error components to be small, for example, smaller than for this mean square error, for this square error, let's assume we want both those components to be less than or equal to tolerance squared, then I need to both reduce my, increase my number of samples so that 1 on n is less than or equal to tol squared. And I need to reduce my mesh size so that h squared is less than tol squared. So in total, I need to make my mesh size proportional to tol, and I need to make my number of samples proportional to tol to the -2. If the cost, as I said, is proportional to the number of degrees of freedom, then the total cost is, we do n samples, so we have a cost that's n times h to the -d, or in terms of tolerance, once I substitute this h here, the cost will grow like tol to the -2 plus d. So if I have a 3D problem, as you would do in the subsurface, that would grow like to the power 5th with the tolerance. So if you want to reduce the cost by a factor 2 only, you need to invest 32 times more work. So this will very quickly become prohibitive. So here's an example of a toy problem in the unit square with the quantity of interest being the flux through the region. We're solving it with a multigrid solver, and we're observing for this rather rough random field that we're using here, we're observing a convergence rate for this mixed finite element solver of alpha equals 3/4. We do have the optimal multigrid cost growth, But if I put it back together, I get that the tolerance in this 2D example grows like 12 to the minus 14/3. And as I said before, if you want to reduce the error by a factor 2, in this case, you need to have the cost grow by a factor 25. And for this right case here, which is a much more realistic application problem, we have we cannot reach the tolerance of 0.002 on the system we were using. So what are the alternatives? And there is a lot of work going on in using polynomial quadrature rules, stochastic Galerkin, stochastic collocation methods you might have heard. But these are all still growing exponentially in dimensions. So for very high dimensions, as I said, that are necessary for the subsurface, you still have to work on the cursive dimensionality, which means the growth in these methods is typically exponential in the dimension. This can be overcome, but it requires a lot of smoothness of the problem. So for example, in this thesis by Jakob Zech. The alternative is Monte Carlo type methods, and to improve the Monte Carlo type methods that I just described. So I said that the current one that the simplest one that I just described, just sampling and averaging, is dimension independent, but it converges very slowly. So you can use better methods, quasi-Monte Carlo, I'm not going to talk about that, or you can use multi-level methods. So let me now give a little bit more detail about the maths behind it, and then the multi-level idea. So just a little bit more detail on Monte Carlo theory and Monte Carlo. So if I'm not so sure how many of you have done deep probability theory courses, but I guess some of the basics you will have done. If I take a Monte Carlo estimator, which is, as I said, sum up n copies of a given random variable x and divide by n, then that's an estimator for the expected value of that random variable. The strong law of large numbers says that it converges almost surely, and it even converges for any function of xk to the expected value of that function of x. The central limit theorem, which applies if you actually have second moments for your random variable, so if the variance of x is bounded, then you can say more. You can actually say that not only does it converge, it converges, in fact, in a very precise way. It converges to a Gaussian. So as you increase the number of samples and you calculate this normalized version of the Sn, then you know that as n goes to infinity, this Sn star actually converges to a standard Gaussian. So not only does it converge to the correct estimate, it contracts as n gets larger like a Gaussian. Which then tells us immediately that the mean square convergence, the mean square error, converges exactly like the variance of our estimator, and that is sigma squared over n. So that's where my result before came from. So the sampling error is simply the variance of the quantity, or in this particular simple case here, the variance of the random variable x divided by n, which is where the n to the minus a half convergence rate for the standard error typically comes from. But you can actually do more. You can actually use Chebyshev's inequality, and not only does it prove in mean square, it actually converges in probability. You need to add this little epsilon fudge factor here, but if you add this little epsilon here, then you can actually say that that it actually converges in probability to the mean with a certain rate again. And if you even have third moments, so if the random variable has bounded third moments, then you can even say how far for a given n the probability density function, the CDF of our normalized empirical random variable is from the Gaussian. So that also converges with 1 on square root of n. And this allows you then to have confidence intervals. And this is where statistics typically comes in. So now I know that for a given n, I can actually say, what's the 95% confidence interval, or asymptotic 95% confidence interval for my Monte Carlo estimator. Okay, so that was just a bit of background on Monte Carlo. And now let me give you the very simple model problem I want to guide you through to show multi-level Monte Carlo. So it's a simple Lotka-Volterra or predator-prey ODE model. So you simply have two ODEs, U1 dot, U2 dot equals this nonlinear combination of U1 and U2, which typically is used to model two interacting species, where one is a predator species and one is a prey species. And you've got some initial condition U0. With parameters theta 1, theta 1, 2, and etc. Now, let's assume, to make it a UQ problem, for simplicity, all the parameters are just 1. Let's assume that the initial condition, so my initial count of predators and prey, say, for example, one of the animals is a very shy animal that hides in the bushes, and you're not so certain about the initial condition, and you would like to study what that means for your current situation or the future situation of the population. And so we're going to model it, for example, with a uniform distribution around a mean value U0 bar, with minus delta delta, a box around this mean initial condition. And the goal could be, for example, to estimate how many chickens do I still have after the foxes have had their play, after time t. So here is a sort of a phase plane picture where you're plotting U1 against U2, and you're starting in this red square. That's your initial condition, and you see that the mean initial condition leads to this black curve, and the other, there's I don't remember, 15 perturbed trajectories that start with different initial conditions. And you see that the outcome on U1 can be quite spread out. So in particular, this guy here is quite far out from the others, and then you can work out, for example, the uncertainty about your prediction on U1 of t. So obviously, this is a very, very simple model problem. I could make this much more complicated. I could have more interacting species. I could have that actually the parameters are time dependent and uncertain over time. So for example, a pendulum can be modeled with the same equations, and you could have the wind affecting the pendulum. But in particular, and this is why I picked it, it's also the simplest case of the epidemics models used for modeling COVID-19. So the SIR model is, in fact, the predator-prey model with a particular choice of the thetas. Okay? So in the very simplest case, this is not the model that most people would use. And in fact, a postdoc of mine has worked with one with an extra component for exposed and another one for hospitalized. So you can just have a slightly different one. But the important bit is that these ODE systems are playing quite a big role in epidemiology. And of course, I don't need to explain to you that they involve a lot of uncertainty. So let's just go back to our maths. So we have our ODE system. Let me just show it again. So it's simply U dot is f of u, two-dimensional with U naught equals U naught. I'm just gonna use an explicit Euler approximation in time. So I let UM denote the explicit Euler approximation of U of t after m time steps of size t over m. And I start with an initial condition U naught of omega, which is uncertain. So by explicit Euler, I'm simply gonna take my previous time step, uj minus 1. I'm adding h times f of uj minus 1, and that's my next time step, uj. I go to my first numerical analysis course. I find out that explicit Euler has consistency order 1. And the output functional we want is simply the U1 component. So that's clearly a Lipschitz. So I said it in a minute. So first of all, we know that the error will be less than or equal to some constant times h. And then the output quantity of interest was just to take the first component U1 of t, which is clearly a Lipschitz functional, and we can simply say that the expected value of q minus expected value of qh for our very, very, very simple model problem is less than or equal to k times h. So I have proved one of the assumptions for my result before, namely that my result before holds with alpha equals 1 in this example. So the bias error is order 1. Now I'm going to use my Monte Carlo estimator as I did before by taking IID samples of my initial condition and calculating the trajectory with explicit Euler with time step size little h. I have my bias variance decomposition that I already stated for you. I invite you to prove this for yourself. It's actually pretty straightforward to prove. So here's a little hint. And if I use that and also realize that the variance of my quantity of interest for a given mesh size h, for sufficiently small h, QH converges to Q, remember, the variance obviously converges to Q, variance of QH converges to variance of Q. So if I make h sufficiently small, I can bound the variance of QH by, say, 10% more than the variance of Q. And I have my bound now for the mean square error being a clean and very clearly defined function of h and n. I can do the same in probability, as I told you, using this asymptotic confidence interval that I described to you before. I can show you also that the probability that the error is less than or equal. The error here, sorry, I didn't define it. The error being the error in modulus of q, e of q minus qh, being less than or equal to the same constant, just I need to have this extra factor 1.96, which comes because of choosing, because I've chosen 0.95% confidence interval. But in both cases, you see that in order to get the error below a certain threshold, I need to reduce both h and increase n. Now, finally, I need to tell you something about the cost. So the cost for this example is in each time step, this simple explicit Euler for this simple ODE has 8 flops. So I can actually give you the exact number. I need to do 8 times number of time steps times number of trajectories flops, which is essentially linear in n and linear in 1 on h. And so if I put that all together, I can basically prove that the total cost with the standard Monte Carlo estimator for the expected value of the number of the first species at time t for the predator-prey model with explicit Euler is growing like epsilon to the minus 3 in order to get a mean square error of epsilon squared. Okay, so to do this, I do exactly what I did before. I set the bias error to be half of the tolerance, and I set the variance error to be half of the tolerance, and then I just rearrange, and I get even the constant in front of my epsilon to the minus 3. So why am I giving you all this? Because obviously with anything in numerical analysis, if you want to design a new method, you first need to have a method to compete against. So this is basically what, for this simple model problem, standard Monte Carlo gives you as the cost. And remember, there is 2 aspects that play a role. We need to make the time step size smaller, which increases the cost, and we need to increase the number of samples. So both of those things grow. And that's why the cost is epsilon to minus 3. So the multi-level Monte Carlo method is now a very simple way to improve on this using variance reduction and using the fact that for most numerical analysis problems, especially in differential equations, we have not just one discretization, but we have a whole family of discretizations. We can choose how accurate we solve a problem. And when we solve it not so accurately, the cost is typically cheaper. When we solve it very accurately, the cost is typically higher. So we want to use multiple hierarchy, a hierarchy of multiple levels in order to reduce the cost, but still get the same sampling error. So the method was originally in abstract terms described by Heinrich, then popularized by Mike Giles in SDEs for math finance, and then in parallel, Chris Schwab and his group and Mike Giles and myself and Aretha, together with Andrew Cliff, extended it to the UQ context. And as I said, I think I've said it now many times, we would like to estimate the expected value of an inaccessible random variable Q via a hierarchy of approximations QH parameterized by H. So okay. So here is just I just made an abstract version of the complexity result that I just gave you for the predator-prey model for standard Monte Carlo. Sorry, I had to remember what this slide was about. So before I gave you a specific case with a specific rate h to the 1 and a specific rate h to the minus 1 for the predator-prey model. But if we have an abstract, an arbitrary problem where QH converges with rate h to the alpha to q, and where the cost grows with h to the minus gamma, then the same proof that I just sketched for the predator-prey model gives you that the mean square error of the standard Monte Carlo estimator for the expected value of q converges with the rate epsilon squared at a cost of epsilon to the minus 2 minus gamma over alpha. And so what's the multi-level idea now? So I told you already we're going to use not just one discretization, but we're going to use a hierarchy of different discretizations. Think again about the predator-prey problem. So in the predator-prey problem, we had the Euler method, and we can just use the Euler method with fewer time steps, coarser time steps, or with many time steps, and therefore more accurately. And just write this simple collapsing sum. So I'm simply writing the expected value for QHL for the finest mesh size as Q of the coarsest mesh size plus differences between consecutive mesh sizes. Now I exploit linearity of the expectation. So I can just say that the expectation can be split up into a sum of expectations, where each of the expectations is now over a difference of two quantities of interest. And another observation here, you don't need linearity of the quantity of interest. So Q of U doesn't have to be linear, because what we are subtracting is the full nonlinear quantity of interest minus the nonlinear quantity of interest on two consecutive grid levels. And so now you ask me, why is computing L plus 1 expected values cheaper than computing 1 expected value? So for simplicity, let's just do as we would usually do with mesh sizes, just take double the size. So let's take m equals 2. And so we take a mesh size 2, 4, 8, 16, etc. So the mesh size is a geometric progression. And then in order to estimate this right-hand side here, we use Monte Carlo again. So we're not using a different estimator as before, but we've split our estimator into L plus 1 estimators and doing Monte Carlo on the individual parts. Now, this is a place where, of course, you can use other quadrature rules. So you don't need to use Monte Carlo here. You can do the multi-level idea also for for stochastic collocation methods or for quasi-Monte Carlo methods. But I'm only going to focus on Monte Carlo. So each individual of these estimators here is now an average over differences between consecutive levels. So here you see the coarsest level is just as hard, but on the next level up, I can't highlight this. On the next level up, we're taking averages of differences. Now, the variance of if we're taking independent samples on all the levels, then the variance of the estimator is the sum of the variances. So this is a simple statistics fact that if you take independent random variables, then the variance of the sum is the sum of the variances. And so the mean square error split that I did before just carries through as we had for standard Monte Carlo, and we now simply get that the bias error or the mean square error is split into bias error squared plus sum of variance errors over the individual levels. And now here is where we're going to make our gains, because if this variance on the numerator here is small, then we don't need a very large NL. And this is exactly where the idea of multilevel Monte Carlo comes in. If we are estimating differences, and these differences are small, then we need fewer samples. So on the finest mesh, we still have to choose our mesh parameter such that this bias error is small enough. There's nothing different to standard Monte Carlo, so we pick that the same way as we did for standard Monte Carlo. So HL is H, and we still have to pick it proportional to epsilon to the 1 on alpha. But why do we get variance reduction and lower cost or lower cost for the same variance? So the coarser problems, remember, our cost grows proportional to h to the minus gamma. And so if I have h larger, then my h to the minus gamma is smaller. And so the cost will actually decrease by a factor m to the gamma from level to level. So if we have a mesh size growing by factor 2 every time, it decreases by a factor 2 to the gamma. And then the variance, the second reason why the cost goes down is that we assume that our quantity of interest converges, which means that the variance of the difference has to go to 0. As a converging sequence is also a Cauchy sequence, and so the variance of the difference goes to 0 as L goes to infinity. And that's exactly why I said before that these variances of YLs become smaller and smaller and smaller as we increase L, which means we can make NL smaller and smaller and smaller as we increase L. Okay, and in fact, you can do that in a very mathematically correct way. You can phrase the cost as the sum of the costs on each level times the number of samples on each level. And you can phrase the variance as the sum of the variances. So if you want to have this sum of the variances equal to epsilon squared over 2, you can solve a minimization problem. You can minimize the cost subject to the variance being equal to epsilon squared over 2 over possible choices of the NLs. And that gives you a formula for how you can decrease the NLs as L goes to infinity. So it gives you an explicit formula for how many samples to choose on every level. That depends on the variance decay over the levels, and it depends on the cost growth over the levels. And given that, you can then, I'm going to skip this because I'm running out of time already. In both cases, in the case where the variance decays faster than the cost increases, your gain that you make is that you essentially, the most work your estimator does happens on the coarsest level. And therefore, your gain is that you essentially do most of your samples on the coarsest level. And so your gain is how much cheaper it is to do a coarse sample. So that's a huge gain. If the cost increases faster than the variance decays, then the most expensive work is on the finest level. And on the finest level, you essentially have variance of YL essentially going to 0. So essentially, it goes to 0 with order epsilon squared. So so you get a gain of epsilon squared. So the more accurate you want to solve it, the more gain you get. And this can be actually phrased in a rigorous abstract complexity theorem, which looks very similar to the one I had before for standard Monte Carlo. So this was the same assumption I had for standard Monte Carlo, namely that the bias goes like h to the alpha. This is the same assumption that I had before for the cost, namely that it grows with h to the minus gamma. And only by making the assumption that the variance of the difference goes to 0 with a certain rate beta, I can then do a rigorous complexity result that states the cost of the multilevel Monte Carlo in comparison, or it states the cost of the multilevel Monte Carlo for all various scenarios of the growth of the cost versus the decrease of the variance. But as I said already on the previous slide, either your gain is that you gain this beta over alpha, which is epsilon to the 2 typically, or you gain essentially that you've completely lost the cost of the solve on the fine grid. So there's no, this is purely the Monte Carlo epsilon to the minus 2. All the cost that comes from solving the samples has disappeared. And the proof for that you can find in those references of this abstract result. Okay, so let me just show you for the predator-prey problem. And as I realized before already when I set the talk, I will probably not get back to the PDE problem. But for the predator-prey problem, let me just finish now why we get this gain with the multilevel Monte Carlo. So as I said before, the two assumptions for the bias and the assumption for the cost, they do not change for multilevel. So we still have alpha equals 1 and gamma equals 1 as in the standard Monte Carlo setting. So we need to basically now look at the variance of the difference. So the variance of the difference is basically the variance of QHL minus 1, which can always be bounded above by the second moment. The variance is just the second moment minus the square of the bias. And so, so this is always bigger. The second moment is always bigger. Now, the second moment, you can use triangle inequality to split it into a second moment for Q minus QHL minus 1, and for a second moment for Q minus QHL. So both of those are now just errors with respect to the exact random variable Q. Now we know how these converge. We have proved that before. Namely, they converge with rate k times HL minus 1. And so the square converges with k squared times HL minus 1. And the same holds true for this guy here. So in total, we get a constant times HL squared. And therefore, we have proved that beta is 2. Now we are in the regime beta being bigger than gamma, and therefore we are in the regime of the first setting here, where beta is bigger than gamma, and so we have now order epsilon to the minus 2 cost, basically. Remember, the original standard one was order epsilon to the minus 3, so we gained a whole order of magnitude in the cost. And this was just for this simple 1D predator-prey model. For the PDE problem, which I'm not going to have time to do in detail, but I'll show you the main result. We will gain 2 orders of magnitude. So here is just to see it in action in a numerical calculation. So the blue and black lines are 2 versions of standard Monte Carlo. The blue one is a slightly improved, so it's a different variance, a different variance reduction technique called antithetic sampling, which is improving by factor 2 roughly the cost, but the multi-level clearly has a completely different slope. It grows like epsilon to the minus 2, while the blue and the black lines both grow like epsilon to the minus 3. So eventually, the multi-level Monte Carlo will be cheaper significantly cheaper than the other methods. You can make the algorithm adaptive because in each step we can actually estimate the variances in each on each level by a sample variance estimator, and that allows you to compute the NLs on the fly. Similarly, you can also estimate the bias error by looking at these differences, because the YLs, remember, are just QHL minus QHL minus 1, and those give you estimators for the bias error. So with both of those components, you can actually design a fully adaptive MLMC algorithm that starts with a coarse or two meshes, a coarse and a fine mesh, and decides itself if it needs to refine more, if it needs to refine more to get the bias down, and it decides how many samples to add to get the variance error down. So this is given here. Okay, so I make it about 54 minutes, 56 minutes I've spent. So let me just quickly say how this extends to the fruit fly that I told you before, so the PDE problem. So in essence, everything extends in the same way. We need to analyze how the error in the finite element approximation grows with age. We need to analyze how the cost grows with age. And we need to look at this, this variance of the differences. If we can bound those three with the right rates, then we will know that the multi-level Monte Carlo estimator will be a much more efficient way to solve this, diffusion problem, or uncertainty quantification problem for this diffusion problem. It will be a much more efficient way. So I need certain assumptions on my coefficients. Typically, we're using Gaussian random fields for our model problems, and that is actually quite a common choice in subsurface flow. Here to give you idea of how these random fields look like. So they are basically, in this case, you really, if what we typically use is the exponential of this, which is called a log normal random field, then you really have to think of the blue regions being in the order of 1,000 to 1,000,000 times smaller values than the red values. And so you really have much more diffusion going on through the red regions than through the blue. The blue you can think of as almost like blockages, and the red ones as channels where it can flow through. Here is two realizations, so as to see that when you sample and solve the PDE, you really have to solve a different PDE. It's a completely different coefficient. And here you see this is a different smoothness parameter. So this is a much smoother field, but at the same time, I've made the correlation length shorter. So you see that you have to also work with different types of random fields. You discretize the PDE with finite elements, and then you can prove, similarly as we did with the explicit Euler discretization of predator-prey, you prove that the quantity of interest converges with the rate, in this case, order h squared, under the assumptions I've made. And then I can again prove for a Monte Carlo estimate, for example, of this quantity of interest, which is here. As we did before, I can prove that the assumptions 5.1 and 5.2 about the bias error, then obviously I've just written that down. So that's basically order h squared. And the cost with multigrid, with a multigrid solver would grow like h to the minus d. I already said that at the beginning in my motivating slides. So basically, we find that the alpha is 2 for our functional here, and the gamma is d. And so if you put that into your, in my abstract complexity result, we get that the cost grows like epsilon to the minus 2 minus, this was gamma over alpha, so it's 2 over d, d over 2. So for 3D, this would be like roughly epsilon to the minus 3.5 or something like that. Now, in the multi-level setting, you would use a hierarchy of finite element grids, and you can assumptions M1 and M3 are again exactly the same as for the standard Monte Carlo, and you need to again prove something about the variance of the difference, and that can be proved exactly in the same way as before, and the beta is again twice alpha. So because we have the square up here, we end up getting that beta is 4, and so in this case beta is 4 and gamma is d. So again, we're in the regime where we end up getting epsilon to the minus 2 complexity. So basically, instead of the standard Monte Carlo, which was epsilon to the minus 2 minus d on 2, we end up getting epsilon to the minus 2. So exactly identical to the setting of the predator-prey problem. Okay, and if you, as I said, I make these slides available. You can look through the rest of the slides. You will see that essentially in all settings for all d, we get a gain, and the gain in the best case is in the order of epsilon to the is of 2 orders of magnitude. Okay, this is just numeric showing that this actually works, that this actually does give the gains, and then there is some outlook how you can even improve on it by using quasi-Monte Carlo together with the multi-level idea. And then the epsilon to the minus 2, which is the red one I just proved to you, can be improved to epsilon to the minus 1. So this blue line at the bottom here is combining a better quadrature rule with the multi-level idea, and here we even get an extra gain of another power in the epsilon. Okay, so here is a bit of further reading. You can find on Mike Giles' webpage a lot of articles to Multilevel Monte Carlo. I'm particularly interested myself, and I find it very important to work in the direction of adaptive finite elements and sample adaptive hierarchies. And then, as I said, you can use other quadrature rules like multi-level quasi-Monte Carlo and multi-level stochastic collocation or polynomial type quadrature rules. I didn't get the chance to talk about the inference problem, the inverse problem, or the uncertainty quantification, and about multi-level Markov chain Monte Carlo. But again, you can find on my webpage and in the full set of slides, you can find literature to the multi-level Markov chain Monte Carlo. So I'll finish slightly late with a few conclusions. So basically, I tried to get the challenges of doing UQ across, and how multi-level methods can help to solve this or mitigate it. I gave you only a very small snapshot of what's available, and it was very biased towards my own research, of course. But I hope that I've perked your interest, and that you also see the high potential with the multi-level sampling methods. Thanks.